Hello, madam. Good afternoon, madam.
Yeah, good afternoon, sir.
Shall we start?
We'll start, sir. Good afternoon. Welcome back to the AICT sponsored 6 days short term training program on the topic Trends and Technologies of Antenna Design and its Research Scopes. Let's move on to the second technical session on the topic Design of SIW based components by Dr. Mrinal Kanti Mandal. Dr. Mrinal Kanti Mandal is an associate professor in the Department of Electronics and Electrical Communication Engineering at IIT Kharagpur. Sir has received his BTech in Radio Physics and Electronics and MTech in Microwave and Millimeter Wave Technology from Institute of Radio Physics and Electronics, University of Calcutta. He was a research fellow at Institute for Infocom Research, Agency for Science, Technology and Research in Singapore, and was a postdoctoral fellow at École Polytechnique de Montreal and Université du Québec at Montreal, Canada. He served as a reviewer of IEEE Transaction on Microwave Theory and Technique, IEEE Microwave Wireless Component Letter, IET Microwave Antenna and Propagation, Journal of Electromagnetic Waves and Application, and Electronics and Telecommunications Research Journal. His research areas include microwave and millimeter wave circuits, antenna and arrays, 6-port receiver, and radar systems. I welcome you, sir, to our STTP. May I invite the speaker, Dr. Mrinal Kanti Mandal, to take over the session.
Thank you, madam, for your nice introduction. Good afternoon, all. So, I hope you enjoyed your lunch, and 2 hours of lecture. It is really long duration, and it will be a challenge for me to keep you awake. Well, so let me share my slide. Well, so today I'm going to present on antennas and other components in substrate integrated waveguide technology. So mostly we'll focus on antennas, since this is a short-term course on antennas. Well, so this is my presentation flow. In the introduction part, first I'm going to present some of our recent works, basically what we are doing in last 3 years, and then we'll start substrate integrated waveguide technology. Now, starting from coaxial cable to in BCB technology, we have microstrip line, coplanar strip line. On the other side, bulky rectangular waveguide. Then why do we need another guiding structure, substrate integrated waveguide? So that I'll discuss. Then what are the design guidelines and how we come to that guidelines? We'll discuss that. Then fabrication issues, power handling capabilities, some miniaturization issues in SIW technology, and then SIW resonator. So resonator is important because it has many applications in one series, like in filter application, in oscillator. There we don't want loss from resonator. Whereas we also have resonant type antennas where we want loss, but in the form of radiation. So some of the basic properties of SIW resonator we are going to discuss, and then on SIW antennas. So if we go through IEEE Explore in last 15 years, there are at least a few thousand papers on this topic: SIW components, SIW antennas, and SIW systems. And among them, at least 1,000 on antennas. So it is impossible to cover all the technologies. So mostly I will focus on the antennas developed here in our group. So this is my group, and this picture was taken in 2018. So number of heads, including our master degree students, PhD students, it remains more or less same, but some of the faces now are changed. Well, so whatever I'm going to present as application examples, so mostly designed by them, some of them. Well, then what we are doing in last 3-4 years. So mostly now we concentrated on application oriented microwave and millimeter wave systems. Most three main topics. The first one is Doppler radar, more commonly known as frequency modulated continuous wave radar, or FMCW radar. So here what we do, we have a transmitting antenna and we transmit continuous electromagnetic wave and illuminate the object under test. Now the frequency of this electromagnetic wave, it is varied over time, usually in at a frequency of kilohertz range. So we need a audio signal generator to change its frequency, transmitted frequency. Now, at the receiving side, a part of the signal is reflected from object, and then when it comes back, the signal is delayed in time domain because of its flight. Then we compare the received frequency with the transmitted frequency at that time, and basically we multiply them by using a mixer, and then it generates the bit signal. And by reading that bit signal frequency, we can determine what is the distance of the object. Other than its distance, we can also determine its velocity. If it has any vibration, then the vibration frequency, vibration amplitude, and also we can track any object by using FMCW radar. So this FMCW radar, it is now becoming popular in consumer market, mostly for security application and different types of indoor applications. So this is an example of 2.4 gigahertz FMCW radar circuit we designed here. And we started with some commercially available chips. So these chips are mostly designed for Wi-Fi communication at 2.4 gigahertz. So we transformed them for our application by using the external circuits. And as you can see in this RF board, we have a VCO unit, we have a PNL loop, and then this transceiver chip, Wi-Fi transceiver chip actually. And all these chipsets, they are controlled by using a microcontroller. We are using STM series microcontroller. And you can see there are several pins. Some of them goes to the microcontroller, some of them are DC biasing, and some of them are simply control pin. So in the second layer, we have the baseband circuit and the controller unit. So I'm showing some of the individual photographs of this component. So this is our audio signal generator, and this is the baseband amplifier for 2.4 gigahertz system. And here you can see response. So in one of these example, we kept an object in front of the transmitting antenna, approximately 10 feet away, and now we are testing it for vibration. So the object is not vibrating, then we don't have any movement in time domain signal. So this signal, this low frequency signal in CRO, and when the object is vibrating, so we have a clear change in time domain signal. In second example, here we also designed a 24 gigahertz FMCW radar circuit, And left side is the RF part, right side is the baseband part, and below it is the microcontroller. We also designed the DC power distribution. So all of these circuits, they are powered from this DC power circuit distribution unit. So some of the chips operate at 1.8 volt, some of them at 3.3, some of them 5 volt, and for some baseband amplifier, we need plus minus 5 volt. So all these voltages are being generated from a 12 volt adapter. Well, second topic, now we are working on it. It's a millimeter wave imaging system. So right now we concentrated on active imaging system, not the passive one. So the object is first illuminated, and then we have a receiving antenna with the beamforming unit. And as the direction of the receiving antenna changes, it samples the received power versus angle. And that's how we can generate the image of received power. Well, so here I'm showing our first imaging system, its components. So we designed one outdoor unit and another indoor unit. And mostly my master degree students, they actually worked on it. And you can see all the components starting from antenna, mixer, low noise amplifier, detector. So all were designed by them. In fact, for outdoor measurement, we designed one 2-axis antenna positioner, and it is being controlled by microprocessor again. This is the motor control unit. And it was our first imaging system. And I am showing image of our department using the developed system at X-band. So what we do, we first use a horn antenna to illuminate this view, and then this antenna we are using as the receiving antenna at vertical position and then in horizontal position to have to decrease the beam width. And that's how we generated this image. This we are using just raw data, and you can see here we have a metal post. It's generating high reflected signal, and here we have a tree. It is absorbing that signal. This X-band signal, not very with the resolution is not that good, you can see. So now we are going through development of a 24 gigahertz imaging system. Hopefully in 1 year we'll be completing it. Well, and the third topic, it is for high data rate wireless system, and the choice is a 6-port receiver. It is actually the heart of the receiver system. It's a completely passive technology. So for this example, it is X-band 6-port network, and again, whatever required for this system for experimental basis, it's like laboratory demonstration, technology demonstration. So this is the detector array we used at the output, and now we transmitted some 1-0 signals. So basically modulated the RF signal with amplitude, and this is the received signal at some distance. It's distorted as seen in CR. Again, mostly this is by our MTech students. Well, so now let's start today's topic. I'm starting with guide instructions. As we know that already we have many different types of guiding structures. They have their own advantages and also disadvantages. For example, rectangular waveguide. So air-filled rectangular waveguide, it is bulky, and if we want to design any components based on rectangular waveguide, it becomes expensive and heavy, but it has two main advantages which is not possible from any other guiding structures. The first one, it is least lossy. If I compare attenuation constant per unit length with other guiding structure, an air-filled rectangular waveguide provides minimum loss. So that's why at terahertz frequencies also, actually the right now only option is rectangular waveguide, where loss becomes significant from other guiding structures. Well, and the second point is power handling capability. It is highest for rectangular waveguide. So you can go for kilowatt to megawatt power level. Again, that is not possible in PCB technology or by using coaxial cable. Well, so here are some examples of guiding structures in PCB technology: microstrip line and a ground-backed CPW line. So these are some of the most popular guides in PCB technology. So the main advantage of this is it is low profile and least expensive. So it's cheaper. Even the fabrication procedure is also it's very cheap, and in university we can easily realize them. We also have a PCB lab, and there we can fabricate PCB based structures. Coaxial cable, if I compare performance with rectangular waveguide or microstrip line, so attenuation constant, it depends actually on the cross-sectional area, what type of dielectric materials we are using inside. So the attenuation can be less than PCB technology. But why it is so popular? Main reason is that we can turn it, we can twist it. So semi-rigid and flexible coaxial cables are available. So that's why with almost all measurement instruments like vector network analyzer, spectrum analyzer, RF source, we see always coaxial cables are connected. So we can easily bend them, turn them. So that is the main advantage. Well, so already then, okay, here are some more examples. Microstrip line with packaging. Okay, this is this bottom line. It represents some of the substrate integrated form of three-dimensional guiding structures. So maybe I'll come back here later. So for now, then we see already we have different types of guiding structures, and they are suitable for different types of applications. And the application, from application point of view, it can be the operating frequency band, it can be power requirement, it can be loss requirement. So depending on that, we can choose from these many options, right? Then why we need a new technology, substrate integrated waveguide? Well, so first of all, if we compare loss performance with the conventional planar technology and the rectangular waveguide, so there is a huge gap. Let me give you some numerical example. For any resonator, quality factor is an important parameter by which we can understand how lossy a resonator is. So for a microstrip line, typically unloaded quality factor, it is in the range of 50 to 200. If we choose the substrate carefully, it can be maybe 300, but not more than that. That is at microwave frequency range. If we go up in frequency scale, at millimeter wave frequency range, it is much less. Even achieving a unloaded quality factor more than 100, it is challenging in microstrip line or any other PCB technology. Well, whereas in rectangular waveguide, a quality factor of more than 10,000 can be easily achieved. Now we have a huge gap between this. One side 100, 200, another side 10,000, 20,000. So in some of the applications, it may require that we can't use microstrip line like structure, but we also don't need rectangular like structure, rectangular waveguide like structure. So maybe a quality factor of 500 to 1000 is sufficient for our application. So we have basically a technological gap between these two extreme technologies. So that is where SIW comes. So from loss point of view, or basically attenuation per unit length point of view. From power handling capability point of view, SIW sits in between the popular planar technology like microstrip line, CPW line, and rectangular waveguide technology. It is just in between. Well, so advantages and disadvantages. So most of these points already we know. For example, microstrip line or CPW line, it's a planar structure. Bottom side, we may have ground, we may not have, but the upper side it's semi-open structure. So if we use any discontinuity, which is obvious in microwave system, well, so what is discontinuity? A straight microstrip line, it is not supposed to radiate as such. But if we introduce any bend, impedance step, open stop, or let's say short circuited via, metal via, or a junction like T junction, cross junction. So all these together we call discontinuities. Now a microstrip line, it supports TEM wave. It can support other modes, but we usually operate in TEM mode only. Well, now at the discontinuities, it may not be TEM mode. It can be other higher order modes or some evanescent mode or some radiating mode. So these discontinuities create a problem, and when we go for any component design or a microwave system realization, we can't avoid these discontinuities. There will be obvious discontinuities. So basically it's a semi-open structure, and because of that we face these problems. Further, if we plot current along the width of the strip, at the edges we have singularities, field singularities, and even we can use a full wave simulator and plot JS along its width, and at the edges current goes to maximum value. Well, so if JS increases in the conductor, we know Joule heating, I square R. So heat loss, because of this conduction current component, it is proportional to square of Js. So we can't avoid high conductor loss. Now if I compare that with rectangular waveguide technology, rectangular waveguide, it is a closed structure. There is no question of radiation, no question of leakage. In PCB, another problem is surface wave. It can generate a wave that propagates along the dielectric in sideward direction, that we call surface wave. So in rectangular waveguide, we don't have that problem. So we can avoid crosstalk. Well, so these are some of the advantages and disadvantages of rectangular waveguide and planar, conventional planar guide. Now, SIW, it comes just in between, and we take the advantage of some of the advantages of PCB technologies like low profile structure, then ease of fabrication. We can fabricate it even in universities using simple setup. Whereas some of the advantages of rectangular waveguide, like almost like a closed structure, then we can avoid, or we can't avoid, we can minimize leakage and crosstalk. It can handle higher power compared to microstrip line or CPW line. So we'll discuss these points in detail. So we have to learn about the mechanism first, or what is the physics behind these points. Then we can work on it further, how to, depending on requirement, how to improve a particular parameter. For example, in some application, we may require a high power handling capability in kilowatt range. Can we use PCB technology for kilowatt range application? So in most of the cases, for microstrip technology or CPW technology, it won't work for kilowatt applications. But SIW, it can be. Well, So these are some advantages and disadvantages. Now coming to system. Well, you never seen that SMD components, it can be passive like inductor, capacitor, resistor, or active diode, transistor, are never used with rectangular waveguide. What is the reason? When we model a diode or transistor, we consider voltage and current. The same thing is true for inductor, capacitor, or resistor. Current and voltage concepts. Well, now we can define current or voltage that is only for TEM case, transverse electromagnetic case. For microstrip line, we can. For coaxial cable, we can. Even for coplanar strip line, we can. But for a rectangular waveguide, which does not support TEM, we can't define an effective current or effective voltage. So we can't use a diode or transistor directly with a rectangular waveguide. Then in microwave system, we have to use them. We don't have any other option. So if we need to use any active components, what we do? We use some transition, rectangular waveguide to microstrip line maybe, and then use that component in microstrip line, and then again you come back microstrip line to waveguide. Same thing is true for SIW, substrate integrated waveguide. Basically, this is a planar form of rectangular waveguide. Well, now in PCB technology, then you see microstrip line, its width is very small. So from miniaturization point of view, then microstrip line, obviously it is much better compared to the SIW or rectangular waveguide. So then what we do in a microwave system where loss is the most important thing, we have to minimize loss. Where, for example, filter or oscillator. For any oscillator, we need a tank circuit. Here is one example. And the phase noise, it depends on the quality factor of this tank circuit. So the quality factor should be as high as possible to obtain a pure frequency spectrum, right? So here we can use SIW technology. And where we don't need SIW, let us use microstrip line. So that is the idea. Then whole thing we can design in PCB technology only. We don't have to go for rectangular waveguide. Well, so that is why actually this substrate integrated form of many three-dimensional structures, it is becoming popular day by day. So here is one more example, a transceiver, a multifunctional transceiver. It's taken from a 2011 MTT paper. So here for the filter unit, they are using SIW cavities. Again, the requirement is lower loss, and insertion loss of any bandpass filter, it directly depends on the unloaded quality factor, and particularly for the narrowband filters, it becomes very important. Well, so that's why they are realizing all other components in microstrip line technology, but the filter, it is in SIW technology. Well, so then we now concentrate on substrate integrated waveguide, how we design it, and what type of wave propagation it supports. So as I said, this is a simply planar form of a rectangular waveguide. Now for a rectangular waveguide with a dimension A by B, the most popular guiding mode is the TE10 mode, and that is the dominant mode. It has lowest cutoff frequency. Well, sorry. So one advantage of using the dominant mode or the mode with lowest cutoff frequency is that we can define a range of frequency or a frequency band of operation over which it will support only one mode. No higher order mode will be supported by the structure. For example, W190 standard waveguide of wider dimension 0.9 inch, corresponding cutoff frequency comes around 6.5 gigahertz. Now looking at the attenuation, it is suggested that you start using from 8.2 gigahertz. Well, I'm coming back to that point later. And then TE20 mode, it is excited at 13 gigahertz. TM11 mode, it has much higher cutoff frequency. So we can use this waveguide till 13 gigahertz, and we are sure that it won't support any other mode other than this TE10. So monomode operation, it is important. It is important for any guiding structure when even we design any component, because different modes, we try to avoid always multi-mode operation or excitation of different modes in the same waveguide. Reason is that different modes, they have different phase velocities. So from left side, let's say I'm connecting one RF source to my guide, and right side I'm collecting power. Now I'm sending a electromagnetic pulse to this guide. Pulse, it has different frequency components. Now inside the guide, if different modes are excited, so they will carry energy with different velocities, and they will reach at port 2 at different time. Pulse shape will change. We also have a second point. When we design any component, it can be, let's say, coax to rectangular waveguide adapter or anything else. We only concentrate on one mode. So impedance matching, then field matching, it becomes impossible to match for all the possible modes. So that's why for practical applications, we always prefer single mode operation. Well, so coming back to the planar form of rectangular waveguides. So what we see for a rectangular waveguide which is supporting TE10 mode, so we have 4 walls, and on the side walls for TE10 mode, electric field value is 0. Tangential electric field value is 0. And on the top wall, electric field is completely normal. So basically then PEC. On PEC or metal surface, electric field should be normal. Tangential electric field should be 0. So it is bounded by 4 PEC walls. Now, if we buy a substrate from market with both side copper, we can use the top copper and bottom copper to realize this top wall and bottom wall of the rectangular waveguide. Then what about the side walls? What we do, we use periodic metal vias. So it's shown here, top view like this. So in this example, in this 3D view, I'm showing some circular metal via. It's easier to fabricate by using a drilling bit, and it is metallized obviously. Now if this pitch via to via separation, if it is much smaller compared to operating wavelength, then whatever electromagnetic wave propagating through this channel, it can't sense this discontinuity. So for this propagating electromagnetic wave, it will work like, it will behave like a continuous electric wall, PEC. Now we can use 2 of them, and then in between these 2, we have a channel, and it resembles the planar version of a rectangular waveguide. But here we have air, and here the dielectric materials remain. So if we start with a substrate, let's say 0.508 millimeter thick RO4003C, then thickness it is defined 0.508 millimeter, and epsilon r it's 3.55. If I start with artiduride 5880, then the filling material has a dielectric constant epsilon r 2.2, and so on. Well, so it is just a planar form of rectangular waveguide, and it will support TE10 mode just like rectangular waveguide. Only difference is that it is now dielectric field, and also its height is reduced. So we can call it a planar form of a reduced height rectangular waveguide. Well, now this gap between two metal via, it determines leakage. So later we'll define a leakage constant, and we'll try to maintain a minimum value, and that define actually the gap with this H to H gap. Now we can have different via geometry, elliptical, or even a continuous wall like this if possible. The circular one, from this point onward, mostly I am going to concentrate on circular one, because we can easily drill a via like this by using a drill bit. Now elliptical or the other shapes, it can be realized by using laser drilling. So for laser, we can actually change the shape of its beam, and that's how we can realize different shapes. Anyway, so obviously for electrical one, it will be much better. The rightmost one much better, because it is almost continuous wall. Well, now if we look at application, so now not just millimeter wave, even people trying at terahertz frequencies. So in last 3-4 years, I've seen some of the papers, they are even using above 300 gigahertz. But of course, if we compare performance with rectangular waveguide, loss is higher. As I said, that we'll be using SIW just like rectangular waveguide. So you can see here the electric field distribution for TE10 mode inside a SIW structure. This is the vector field over cross section, and this is the top view of time average scalar field component. So it propagates in this direction. So here are some structures we are going to discuss in details later. A bandpass filter, then 1:8 power divider, diplexing antenna, directional coupler, all realized in SIW technology, and all of them are actually published paper from our group. Well, so I took this term loss many times. So then let us first understand what are the sources of loss. If we know the reason, then we can minimize it. So why we are coming to SIW from microstrip of CPW line? One of the main reason is lower loss. So that's why I want to spend some time on this particular topic. Well, so for any structure in PCB technology, we face mostly 3 different types of losses. One of them is dielectric loss. It is due to dielectric polarization. The second one is ohmic loss, or sometimes people call it metal loss or conductor loss. And the third one is radiation of surface wave loss. So actually then propagation constant gamma, it is alpha plus J beta. We have some attenuation of weight. For simplified analysis, in most of the cases, we neglect alpha, but practically we have a finite alpha value. And this alpha, it is a combination due to these three different factors. Alpha due to dielectric, let's say alpha D. Alpha due to conductor loss, let's say alpha C. And alpha due to radiation and surface wave loss, alpha R. So it has then three components. Anyway, well, just for one information, so I have actually too many slides here, and I'll be skipping some of the parts. So you please feel free to interrupt me. You can switch on your microphone and you can ask me question whenever you wish. Otherwise, I'm just going to skip some of the parts. Well, so the first one is dielectric loss. We all know that permittivity is a complex quantity represented by epsilon dash minus j epsilon double dash by a negative sign, so that when we calculate power loss, it becomes a positive quantity. Well, so we can define a parameter to quantify this dielectric loss. It is due to dielectric polarization, so I'm not repeating that point. Now, we can quantify for quantification. We can define a parameter. It's called electric loss tangent, and to do that, we start from Maxwell's curl equation. Curl H equal to J plus del D delta. J is sigma E. Now put the value of D here, considering a linear variable. So then, for a time harmonic electric field, we have j omega epsilon dash E, one component from that time dependent term, another component omega epsilon double dash E. So we see it is real just like sigma, and we know for finite sigma we have loss, but this is conduction loss and this is dielectric loss, different. So since they are both real terms, so we can put them together and it will have similar effect like sigma, and that's why we say that from this imaginary part of dielectric of permittivity, actually we have the loss. Lower is better. Epsilon double dash, it should be low to minimize dielectric loss. Then how we define this parameter loss tangent? It is equal to lossy reaction by lossless reaction equal to omega epsilon double dash plus sigma divided by omega epsilon dash. So this term does not provide any loss, imaginary term. Now, if I assume epsilon dash and epsilon double dash, they are not function of frequency, then we have a additional term, omega into something plus something divided by omega into something. So with frequency, increasing frequency, loss tangent should decrease if I look at this term. But practically we see that loss tangent actually increases with frequency. Well, the reason is that epsilon double dash, it increases with frequency. Now, for most of the dielectric materials we use for microwave circuits, they are not magnetically susceptible. So for this magnetic loss tangent, mostly we discard this term. But if we use some ferrites based material, or if we have a trace of nickel or iron, then we can't avoid this term. Anyway, so for now, let us discard. Next, conductor loss, as we all know, it is same as Joule heating because of the current, and it's proportional to square of current. So this current is the conduction current component. not displacement current. Well, now alpha C, we can define this attenuation constant due to conductor loss per unit length. It increases with frequency because surface resistance, it increases with frequency. It is equal to square root of omega mu naught by twice sigma. So what is the reason why surface resistance increases? So we know the concept of skin depth here. Let's say it is a current carrying wire and it's supporting alternating current, then we can use that eddy current concept, and we see that if we draw current density over a cross section, it is highest on the surface of the conductor, and as we go inwards towards center, it decays exponentially. So how fast it decays, to quantify that, we define a parameter, we call it skin depth. The depth below the surface of the conductor at which the current density has fallen to 1 by E times of the surface. And this delta is such a function of frequency. So in other words, we can say if we go to higher frequencies, so basically we have a filament-like structure. We can't utilize this whole conductor for current conduction. It is concentrated on surface, so the thickness, it is decreasing. Again, from basic Ohm's law, resistance will increase. So we can have some numerical values here. For copper, at 10 gigahertz, it becomes 0.66 micrometer, it's less than 1 micrometer. And at 100 gigahertz, it becomes just 0.21 micrometer. That's really thin, and that's why surface resistance is so high. And this is the reason why we can't use a single metal wire to conduct microwave frequency. We can take the example of that 50 hertz line shorts we use in our home application to supply AC power to our fan, bulb, refrigerator with a 50 hertz signal, right? And for that we can use single conductor. So because you see at 50 hertz, skin depth is 8.5 millimeter. So if I use a wire of diameter 1 or 2 millimeter, it is almost like uniform current over the cross section. But this is not the case if we go to microwave frequencies, and that is the reason why we can't use simple wire for microwave power propagation or simple wire for interconnect. And that is the reason why we use coaxial cables, microstrip line, and other PCB structure. So basically, in those structures, metals we use like boundary condition to guide the electromagnetic wave. Actual energy, it lies inside the substrate material, not the metal. So whatever part remains inside the metal, it is actually undesired part. We don't want that. Anyway, we may have another important conclusion from this relationship, J equal to Js into e to the power minus d by delta. Well, when we go for metallization, let's say for PCB substrate, how much metal thickness is ideal for us? You see that figure, it did not come arbitrarily. It came from this relationship actually. So what we see, we have similar relationship for RC circuit, time constant, RC time constant. We have similar expression. So if we compare with that, if we go a distance of 5 times of skin depth from the surface inside, so it is less than 0.1% of the surface value. Or in other words, we can say that a metal thickness of 5 times of skin depth at the lowest frequency of interest is sufficient for our microwave applications. It can be for PCB material, it can be for the via, which is becoming important issue for SIW. So the metal thickness at lowest frequency will consider at least 5 times of the skin depth. That is sufficient for our applications. Well, now another important point. So in textbooks, when they derive this expression, in most of the cases you will see that they consider a smooth surface. Okay, but practically, if we look at a metal surface for PCB material, I'm saying, so it looks something like this. It is not smooth at all. So of course, it's a relative term, smoothness. Now, a typical value for, let's say, the substrate which comes from Rogers Corporation, it can be 0.1 to 0.5 micrometers. Well, that is quite small. But if I compare with skin depth, at 10 gigahertz, it is already 0.66 micrometer. It becomes comparable to this. Well, then, actually, the attenuation constant due to conductor loss is much higher. And we have a closed form expression for this. Alpha C dashed, considering a capital delta as the RMS surface roughness, and small delta is as the skin depth. Then alpha C, this is considering smooth surface, into 1 plus this additional part. And here I'm just plotting that equation to give you some idea that if I consider a smooth surface, almost no attenuation. And it's 2 dB per meter. And this is for an air-filled waveguide, where we don't have any dielectric loss or surface wave loss. Now, if I introduce surface roughness, you see how it is increasing. For capital delta by small delta is equal to 1, it becomes almost double. So this is a reason, if we don't model this surface roughness in our simulation at millimeter wave frequencies particularly, actual insertion loss in measurement will be much higher. It can be 2 times or more than that. The same thing is true for dielectric loss also, even though I did not discuss here. Well, the next is radiation and surface wave loss. It mostly comes from unwanted mode, so I don't want to discuss in details this one. And later, if you are interested, you just ask me. Well, now for SIW. SIW, it's a PCB based structure. Then we can't avoid alpha C due to conductor, alpha D due to dielectric. Now, if I assume it's a closed structure, we don't have any surface wave loss as such, or no radiation loss. But we are using a periodic structure. So if I go back to this picture, it is not a continuous wall like a rectangular waveguide. So we may have leakage and we can't avoid it, but we can of course define some numerical figure, and we will try to keep this attenuation due to leakage below that. So now then alpha, it is revised as alpha L due to leakage plus alpha 2 plus alpha C. In addition to that, we also have band gap effect, since we are using a periodic structure. Well, it comes at higher frequencies. Then, considering these points, what should be our design steps? So before that, we did not discuss about leakage in detail. So let us spend some more time on it. Well, so whatever formula we learned for rectangular waveguide for TE10 mode, for example, the formula for cutoff frequency, formula for beta, and phase velocity, whatever, we can apply all of them for SIW structure. But there is an issue. What is that? Its height, it is defined. Substrate material or the filling material, that is also defined. Now, what is the separation between these two side walls? That is not defined. What I mean that if I want to use formula for cutoff frequency, in the cutoff frequency expression we have a term which define the separation between side walls. Let's say that is A. Now for this structure, how we will be defining A? Is it from center to center, or from inner edge to inner edge, or from outer edge to outer edge? It actually depends also on P and D. So let us define it as a parameter which A effective, which is related to this D value, P value, and this A value. A value is center to center, here to here distance. Well, now if I increase this gap, obviously the leakage will increase. So we are plotting this leakage loss versus P by lambda. For a given D, if I increase P, basically you are increasing gap, the loss will increase. Same thing true for a given P. For a given P, if I decrease D, gap is increasing, so loss will increase. Well, another important point, attenuation. That is important. That's why we came to SIW technology, a microstrip line. Well, if we go back to air-filled rectangular waveguide, this alpha value due to conductor loss, it is already plotted in DM Pojar's book. So at the cutoff frequency, it goes to infinity, then it decreases exponentially. Now, what about alpha D? Alpha D, that increases with frequency. Now, if we have dielectric filled rectangular waveguide like SIW, and we plot alpha versus frequency, it looks something like this. So for this waveguide, the cutoff frequency is below 18 gigahertz, and look at the variation. So first it decreases, comes to a minimum value, then slowly it increases, mostly because of the increased dielectricity. So if I concentrate on minimum loss, we have an optimum value, optimum dimension of the guiding structure, right? So approximately this minimum alpha, it is at a frequency which is 1.5 times of the cutoff frequency. 1.5 times of the cutoff frequency. Now for SIW, we have the flexibility that we can choose A. This is up to us. It's not like standard rectangular waveguide where the broadside dimension already defined. So then if we know what is my center frequency, accordingly I can choose the dimension. So we have that flexibility. Well, so we have an accurate formula, 1.5 times of FC, that is like a thumb rule, and this formula is more accurate. It defines where alpha C is minimum, closed form expression. What about beta variation? We know any guiding structure is dispersive. Same thing is true for SIW. Now at cutoff, no propagation, beta is 0, then beta increases. So rather I actually like a term beta by k naught. versus frequency. So it provides more information. Well, let me compare two cases. Let's say we have a reduced height rectangular waveguide. B dimension is fixed, thickness that is also fixed, and it is air filled. Now we know for TE10 mode, it is always the first wave. What that means? Lambda G, it is more than lambda naught. So then beta by k naught, beta is 2 pi by lambda G, and k naught 2 pi by lambda naught. So then if I calculate beta by k naught for air filled rectangular waveguide, it is always less than 1. That is interesting. So then this beta by k naught equal to 1. This is the line which separates first wave and slow wave region. Below this, it is first wave. Above this, it is slow wave region. For some application, this understanding is important. Well, now for SIW, the same dimension, broad dimension, let's say B, but now instead of air, we are filling it up with some dielectric material. Then cutoff frequency, of course, it will decrease by a factor of square root of epsilon r. Not only that, if I plot beta by k naught, then if we look at the curve, it crosses beta by k naught equal to 1. So it has a first wave region as well as a slow wave region. At this crossing point, it is actually defined by the dielectric constant of that filling material. Well, now coming back to design again. So what should be the ideal P value and D value? P is the pitch, D is the diameter of circular metal here. Well, so D cannot be, of course, more than P. So this is unrealizable region. Now we can define our required leakage constant, and we want to keep that leakage lower than that. In this example, what we consider alpha L by k naught less than 10 to the power minus 4, then it is defined by a straight line by this, and at higher frequencies we have band gap regions. Then we can choose any D, any P value from this region. So this is the region of interest. We can choose any D and P from this region. Yes, so then the design rules. We have band gap effect to avoid that P by lambda C should be less than 0.25. Lambda C is the cutoff wavelength. To keep alpha L by k naught less than 10 to the power minus 4, P should be less than equal to twice D, or this gap, its maximum value is D. And mechanical rigidity, P by lambda C more than 0.05. In addition to that, if we want to use all those formula for TE10 mode in rectangular waveguide, we need the effective width. So we have recently a more accurate formula. So A effective, it is A minus this value. A is midpoint to midpoint via separation. Well, some of the, okay, so finally, what is the design step? Then, as I said, first you note down what is the mid-band frequency. If we are asked to design something for the 24 gigahertz ISM band, then the bandwidth is 24 to 24.25 gigahertz. I will consider the center point, and we will calculate all the parameters with respect to that. Now I want attenuation to be minimum at center frequency. Then Accordingly, I have to, the first step, I need to choose FC, which is F naught by 1.5. Once we have that, then what is the required A effective from formula? Well, so this part is done. Next, choose D and C from this. So we have two limitations. One is coming from leakage, another one mechanical rigidity. So it can be anything in between this. So till now we considered only A effective. Now I have to find out what is the actual midpoint to midpoint separation. Now we can use either this formula or we can use also this formula. In that expression I use this one. Well, now fabrication issues. In short, all the metal pattern, whatever required on top or bottom surface, we can realize that by using chemical etching or mechanical milling. So we have also milling machine here in our PCB lab. So I'm more interested to discuss about how to realize via. We can have metallized via or hollow metal via. So what we do here, first of all, we try to avoid this via hole overall. Okay, I'm coming to that point later. So let me first discuss about this via hole. Simply we use drill bit. It's a CNC, computer controlled milling machine. So it uses drill bit, and that tool, what is the tool bit, its diameter that we can choose, and then we first drill this chain of via. Now once this via is drilled in PCB, then if I look through it, we can see other side, and on the side walls of the cylinder we can see the substrate. If it's white color, then we can see white color sidewalls. Now I need to deposit metal on it. It's not easy to deposit metal on dielectric material. We have to go through some special procedure. So in Professor Keu's lab, actually when I worked, it's 8-9 years back, that time they used sputtering. So that provides a few nanometer of metal on dielectric. Here in IIT Kharagpur, we are using a 5-step chemical procedure we call the initiator. So that does the same thing. It deposits metal on the side walls. Thickness is just a few nanometer. Sometimes even after that chemical procedure, if we look at the structure, metal thickness is so thin that we can't distinguish from dielectric actually. The slight color change like that. Once it's done, then standard electrolysis. We put it in a electrolysis bath, and we have means we know that what should be the deposition thickness. It should be at least 5 times of spin depth, and you can see actually this middle part. This color looks different. This is the deposited copper actually. So now our procedure, it is not that great. What do I mean by that statement actually? We have seen in our step it's a cheaper version actually. So in our case, if the hole diameter it is more than substrate thickness, we don't face any problem. But when the hole diameter is less than substrate thickness, then most of the times we face problem here. So now in fact we are trying to avoid this, and whenever absolutely necessary we use this metal here. Otherwise what we are doing, we are using simply dielectric cutting. Maybe I can show you some. Okay, these are some old structures actually where we were using metal vias. Later we can. Yeah, here we have one structure. It's a 24 gigahertz array antenna. So it's everywhere copper deposited, and after that, actually, our technician forgot to polish it. Means we have to use some other dielectric deposit on it so that it is not oxidized. So because of oxidization, it became black. Anyway, so if we look carefully, you see this part, its substrate is cut completely, and then we have a side wall. So on this side wall, it is easily accessible from outside. Now we are going through the chemical steps, and without a miss, actually we can deposit metal here. We don't face any problem. But when the VI is in the middle, then we are facing the problem, as I said. So where absolutely necessary, then for now now we move to actually higher frequencies, mostly doing 24 gigahertz and above. So we are inserting wire simply. Well, so it is more than 1 hour. Let us take a few questions better, and then I'll come back here again. So you can switch on your microphone and let us take a few questions. 2 hours, really long time.
Hello, sir.
Yes, please. Please go ahead. Yeah, please go ahead. I could not hear your question.
Sir, SIW thickness is very, very small compared to port thickness. How to interface with the ports for measurement?
I'm sorry, I could not understand. Once more.
Sir, that the SIW is very, very small. That antenna size is very small.
Okay.
That port size is compared to antenna, port size is very large.
Yeah. It creates a problem. It
Problem,
was
yes,
better.
sir.
It's a really problem, and but I can suggest you some techniques actually, and we could have a discussion session better. So I need to discuss several points. Yeah, so first of all, when you are going to measure antenna, you have to be very careful about, means you can't simply connect some arbitrary connectors. And whenever you are connecting the connectors, you better look at the electric field orientation. That is important. So depending on that, so you see electric field, if it is parallel to your metal surface, then it will interact most, right? So then the port SMA, you will be using a straight SMA or a 90-degree bend. You decide based on that, so that it interacts least with your incident electric field. That is one of the points. We also have different sets of connectors. Sometimes you see the end launcher SMA, the support, it is much wider than the coaxial part. So we can use a coaxial cable connectors, which is long enough. Then we use the SMA connectors. Did you understand this point? So coaxial cable connectors, its dimension cross sectional is small compared to a direct SMA connector.
Yes, sir.
So this type of techniques are there. You see in this example, let me show. Yeah, here intentionally we took the port completely in a different plane. It's a 24 gigahertz antenna, and we are using SMP, which is much smaller compared to T connector. And not only that, we are taking it completely away. You see, the slot, it is in other side. So when you are connecting port, actually you have to be very careful about that. You have to keep measurement in mind.
Okay, sir.
Any other question?
Can we use EMC coupling in this case?
What coupling? Sorry,
EMC coupling.
it means electromagnetic coupling. You are saying?
Yeah. Put a line
Electromagnetic.
below and then coupled.
Yeah, it can be electromagnetic coupling. It has its own advantage, its own disadvantage. So depending on configuration, then you have to choose. For this one, I have a single pit point and I want to excite a 2 by 2 array using a single pit point. So for this one, I can't use directly EM coupling through a slot.
But it's a single unit you can possibly try.
Yeah, of course we can. But the moment you are introducing a slot or something, it is actually loading your resonator. That also you have to keep in mind. Your resonant frequency will change, your mode can change.
But what happens is this radiation due to the probe can be avoided when you use the slot coupling, EMC coupling.
EMC coupling, again, it depends on your structure. If I use a microstrip line resonator, it can radiate.
Yeah, that's true.
It depends on your configuration.
Yeah, that's true. Thank you.
In fact, if I use particularly at higher frequencies, if I use another substrate layer, it will actually excite more surface wave. So instead of getting advantage, it can be disadvantageous.
Disadvantages. Yeah.
It depends on, actually, we can't have a general conclusion.
So mostly you will use only coaxial here in general for all these SAPs for feeding.
Yeah, coaxial is the ultimate target since coaxial cables are connected with VNS.
Yeah, that's true.
That is only reason.
Yeah. Okay. Thank you.
If you have waveguide based VNA, then we can go for waveguide.
That's true.
Yeah, or for all old VNS, let's say 15-20 years back, above 60 gigahertz, it was only waveguide based.
Correct.
Mrinal sir, we have 2-3 questions in the chat. Shall I read
sure.
it out?
Okay, sure. I can also go through it. Oh, in DRDO and ISRO, ISRO, Dr. Bheridi is here. Well, so he already answered. Yeah, in ISRO, I know particularly Dr. Bheridi is from Bangalore. So in SAC, I visited and they are using SIW structure. They are fabricating it. Probe inductance, there are many points actually, not just one point. It's a general comment type, means we have to go case by case. But we have standard parasitic compensation technique. It's simple impedance matching, what we learned actually single step matching. We have to nullify JX part, either you can do it in series, you can do it in shunt, and use similar sort of geometry to do that. Well, at terahertz frequencies, as I said, that most preferred structure is the rectangular waveguide because loss becomes one of the most important issues. But at terahertz frequencies, let's say we're designing a mixer. Now, I discussed this point already. In waveguide, we have TE10 mode. We don't have any other option. We have to use some sort of TEM line. So you will see that first they will put the active device on a microstrip line, then that circuit they will insert inside waveguide. So mostly rectangular waveguide is preferred, but in last 5 years there are few papers where they are also trying SIW. But whenever the moment I introduce SIW, it will be lossy. So So SIW, it is just a term. So you see, reduced height waveguide, it is already there more than 30 years. Well, if there is no other question, then we can go back to presentation. And I have taken, as I said, I have too many slides. So 3 years back, I think we organized a course on SIW, and I'm simply sharing my slides, updated slides from that. So now I have to reduce my 8 hours lecture to 2 hours lecture. So I'm trying to do that basically. Well, so let us discuss a few points on power handling, because that is also important when we compare with PCB technology. So before that, let us understand what are the limiting points. Well, the first 2 points, it is valid only for rectangular waveguide, air-filled rectangular waveguide, multifaction and ionization breakdown. Now for SIW, we are using it's like dielectric field waveguide. So this last 3 points becomes important for SIW. Passive intermodulation. So for most of you, most probably this term is not well known. When we introduce, okay, so let me start with simple mixer. In different applications, we use nonlinear devices. Whenever we need to change the frequency, mixer is one of the examples. So there, as nonlinear device, either we introduce PN junction, or it can be a metal semiconductor junction. But what about two different metals? So when we have two different metals, there also we have a barrier. In most of the cases, it is so small that we simply neglect it. But consider a situation like, let's say, you have a transmitter where you are transmitting kilowatt order of power, and inside the guiding structure we have some impurities. So basically 2 or 3 different types of materials, and because of that we have small barriers, so which introduces non-linearities. It is small, and because of these small non-linearities, it generated undesired frequency components, maybe from kilowatt, it may be in watt range or maybe in milliwatt range, so we can neglect it. But when it comes back to receiver, it may happen some of the frequency this undesired frequency component, it is falling in my desired band of the receiver. And for the receiver chain, we use very high gain, sometimes 60 dB, 70 dB of gain. Now this milliwatt power, or this let's say nanowatt power, it is amplified to milliwatt or watt range. Then it will saturate receiver, and we can't track our desired signal. So that's why passive intermodulation, it is important. Even though we are not using any active component, this is just because of impurities we have these issues. Well, intermodulation products we have when we have more than one frequency component. Next is electric breakdown. So when we buy Rogers material, if you go through data sheet, they will always give a parameter that how much maximum electric field it can tolerate. It depends on material. It can be 15, 16 kilovolt to even 35, 36 kilovolt per millimeter. It depends on material and also shape, because shape determines electric field. Anyway, so we can't exceed that. Then we have electric breakdown. Now, inside the structure, we have different sources of loss, conductor loss, dielectric loss. They are finally going to generate heat. So in steady state, we have to somehow dissipate this heat. If there is heat accumulation, there will be local temperature rise, and then we may have thermal related breakdown. For example, melting, glass transition temperature, then burning. Burning means it's reaction with oxygen basically. So what is glass transition temperature? Usually, I can let me give you that Rogers example. Usually, let's say we are designing something on artillery 5880. Now temperature is rising from 40 degree to 80 degree to 100 degree, 140 degree. So if this temperature rise is small, when we of course with temperature dielectric constant will change, other parameters will change. But if we come back to our initial room temperature, then all the properties also come back. So it's a reversible procedure. It continues till a given temperature. If you exceed that temperature, then its dielectric properties change permanently. Now after that, if we come back to room temperature, we can't bring down. It's not reversible anymore. So that temperature is called the glass transition temperature of any dielectric material. Let me avoid multiplication. So if you are interested in any topic, so please switch off your microphone and ask me question. Also, just let me give you some conceptual idea how we do power handling analysis in brief. Okay, this is just introduction. Well, so the main problem, it comes because of heat generation from the structure, and the second one, the electric field value, peak electric field value. Well, now we, depending on application, we may have two different situations. In one case, it's a CW wave case, continuous wave case. So there we are interested on average power handling capability. And in the second category, where we transmit pulses, so very narrow pulses, in most of the time it is not transmitting anything, conducting anything. So there time period is very small, we don't have enough time for heat dissipation. Then we are mostly interested on peak power analysis. Well, so in the average power analysis for CW case, what we do, we calculate the heat generation inside structure that we equate with heat loss per unit area. Now for SIW structure, how it can lose heat, it is due to convection if it's in air, or we may have radiation which is coming out from the metal surface which is supporting it. Then we equate these two terms, we can calculate them, and from that we can predict what is the highest average power handling capability for SIW. I'm just giving some numerical example without going through it. Well, so here some numerical examples of average power handling capability, its variation with frequency. H, it represents the substrate thickness or the thickness of SIW. Now, if we have a thin dielectric substrate, then heat generation is more. So that's why you see average power handling capability is lower. It also decreases with frequency. Well, I can explain it, maybe this point is interesting. We are considering reduced height waveguide. I think all of you can see my drawing. So this is waveguide 1 and this is waveguide 2. Sorry, I'm using my mouse. Also, what I tried, that B dimension it's same, but thickness they are different. Then their cutoff frequencies same, because wider dimension, dielectric material, that remains same, and the cutoff frequency is determined by these two. Now, what about the heat generation? Conductor loss, it depends on Js, conduction current. Js, where it is generated? On metal. Now, if I look at TE10 field distribution, electric field is perpendicular, right? And it is in this direction. We have a maxima here, and it varies sinusoidally left to right on the side walls is G. What about the magnetic field? Magnetic field, it forms loop surrounding this electric field. So it's on a perpendicular plane and which is parallel to broad side wall. Well, now how we calculate Js on metal surface? If we recall what we learned in UG class, N cross H, that provides the Js. N cross H, that means the tangential magnetic field component. So Js, it is proportional to tangential magnetic field component. Now if I look tangential magnetic field